Okay, we are officially in the pre-calc part of the, well, part of the year, but part of the unit. As we move into this, just so you know, this is, meant to be delivered after, not after another year, basically, of of school. So you might see some stuff in here that's kind of review of the Algebra 2 part, which I just left in. I think it's going to be a good idea, and I think it's also going to help you see like when it's needed as it comes up here as part of the pre-calc. This part of the unit is actually newer than the Algebra 2. I don't know if that matters to you, but it might explain some of the surprise I might feel from time to time. Like, oh yeah, they changed this. Okay, so that textbook reference makes no sense. But I kind of warned about what we'd be doing here in PreCalc, which is the counting principle. So we're going to be getting into the combinations, permutations stuff, being able to count possibilities before we turn them into probabilities. Okay, and appropriate shortcuts is a big one too. I like how they say, I like how they say that here. Appropriate shortcuts. 8 pieces of paper are numbered 1 through 8, placed in the box. One paper is drawn at random. The piece of paper is replaced. Then a second piece of paper is drawn. Finally, the two numbers are added. How many different ways can a sum of 12 be obtained? This is almost like rolling dice. You got to think about the possibilities we could get for these two pieces of paper. With dice, we did things like, it was almost like coordinates, right? We were doing this kind of thing and filling out a table. How many sums of 12 are there? Well, the lowest one would be 4 and 8. And of course, we can have that backwards, 8 and 4. 5 and 7, and 6 and 6. So I believe there would be 5 ways. Okay. 8 pieces of paper, same thing, not replaced. Then it's a little bit different. Then we can't have the 6, 6. So I'm just gonna say it this way. Hey, appropriate shortcuts. So it's just gonna be 4 ways. Okay, that's really no big problem yet. Okay, most probability problems will require you to count the number of ways a particular event can happen. Right, this whole probability is usually the number of successful ways it can happen over the total, and that's both of those things involve a lot of counting, or potentially involve a lot of counting. The counting can be difficult, I guess, is what I should say. Fundamental counting principle. This is the thing about multiplying. This was the same fundamental counting principles. This is that first time I guess we're talking about review from Algebra 2. There was I guess in Algebra 2, the first question was like the jerseys and the pants and the socks. We just multiply. It's it's when we're doing this kind of thing. That happens a lot in counting things up. Okay, so this is exactly what's happening here. But of course, they're going to be a little bit more ramped up because we're a little more advanced now. And this is right now just kind of review of the unit we would have done a year prior if we were taking Algebra 2 and then pre-calc. Okay, Singapore is 3 letters, 4 numbers, and end with a letter. So it's letter, letter, letter. Then it's, I wrote a problem about this once. It's more to it than this. Like the first letter has to be S, and the second letter can't be a vowel. I mean, there's some more restrictions, but yes, this is what they look like. And then there's a letter. How many different license plates can we have? Well, for the letter choices, there are 26 letters for each, including that one. And for the numbers, we're going to actually have 10, because if you think about the digits 0 through 10, or 0 through 9, there are 10 of them. Multiply all this stuff up, it's a lot. It's going to be 26 to the 4th power times 10 to the 4th power, which is, give me a second, something like 4, 5, 6, 9, 7, 6, and a bunch of zeros. That's a 0. So like 4 billion something? No, I don't know. 4 trillion something? Great, it's a lot. Okay, counting problems where restrictions are placed, deal with the restriction first. We did this in the Algebra 2 stuff when we were talking about like, it was like the warm-up in last class. It was like, rearrange these letters, but the first letter has to be, well, I guess this is what we see here. The first letter has to be a vowel, and the last letter can't be a vowel, like that kind of stuff. If we do this first, we're not going to have any problems later in terms of like a branching tree kind of situation. If we just get those out of the way first, it will be easier, basically. It will account for all the possibilities we need to account for without a wrinkle and without having to recount or, be silly about it. Okay, so determine the total number of different 4-letter arrangements can be formed by using the letters in the word English. Now again, we're going to come up with this later, but right now all those are different letters, which is really helpful. So 4 letters, no restrictions. So letters can repeat and all that kind of stuff. So there's 7 different letters. Any one of those. Oh, is it arrangements? Oh, when they say arrangements, do they mean they can repeat? Yeah, when they say arrangements, okay, let's just talk about this now. They say arrangements, it means we're just moving things around. I can't use the same letter again if I'm just repeating it. Imagine like these are Scrabble tiles, or imagine these are on cards. Arrangements is just shuffling things around. So that implies no repeats. Sorry, I have to be sure about that. Would I tell you that on a test if you asked me? I probably would. First letter must be E. Okay, we're going to deal with that restriction first. There's one choice for that, and then after that, we only have this many choices. I should probably be multiplying these up. This is 840. This is divide that by 7, so this is 120. First and last must be vowels. Okay. So how many vowels do we have? We have an E and we have an I. First one can be either one of those, but then the other one is kind of determined by that. Then after we take 2 letters out, we're left with 5. So 5 and 4 come down. After that, we've got 40. All right, and then no letters are, the arrangement must contain G. Must contain G. Well, there's a few ways we could do this. Let's think about this. What if G was in the first spot? Or, so I'm going to use a plus. What if G was in the second spot? Or, there's probably one way to do this. What if G were in the third spot? I didn't put it in the third spot. There's the third spot. And what if G was in the last spot? Okay, in all of these, the remaining letters are going to go 6, 5, 4. You might have thought about this a different way. You might have thought, like, think about how this is going to reduce now. It's like I'm taking 6 times 5 times 4, and I'm taking that whole thing times 4 because there's 4 of these. You might think there's 4 ways I could arrange where the G goes. And after I do that, I fill in the rest of the letters with 6, 5, 4. That's fine. This turns out to be 480. Okay, permutations. This is where we see the exclamation points start to come in. This is n factorial, which looks like they're not really explaining that here, so I'll talk about this. This is read as n factorial. And factorial is defined to be n times n minus 1 times n minus 2 times ... times 2 times 1. We are multiplying all the numbers from n on down to 1. Okay, and you're going to see this a lot, and you're going to ask yourself this a lot. I don't know that this is the only way to think about this, but people are going to keep coming up with this as a question a lot. Does order matter? When does order matter? Order matter. You're going to get sick of hearing the term or the question, order matters. So I try to explain it in other ways. But yes, it's the same thing as order matters. Another way I like to think about counting permutations is like if you're counting collections of things and the arrangements, if they look different, do we count them different, or we just care about who's in the collection? If we just care about who's in the collection, it's not a permutation. But if we care about what the arrangement looks like, then yes, we do care about counting it as a permutation. So like they say here, if we want to count A, B, C, and CVA differently, I count them as a permutation. There's all kinds of questions, and we're going to get up to them later. They're called combinations, where A, B, C, and CVA in this situation would count as the same situation. But if they count differently, then I'm going to count it as a permutation. Okay. An internet site access code consists of 3 digits. So this is like a password kind of thing. Yeah, and if you typed your password in the wrong order, it wouldn't work, right? So this is a situation where yes, we do want to count this as a permutation. All right. So in this one, the numbers are 3, 5, and 7. If the digits must be entered in the correct order, how many ways could it possibly go? Well, yeah, the first time you do this, it's probably a good idea just to kind of do it. 3, 5, 7. Let's try to be systematic about this. Switch the 7 and the 5. Let's start with a different one. 5, 3, 7. Let's kind of go in order from least to greatest. How about? And then starting with the 7, it's going to be 3 and 5 and 5 and 3. Hopefully that felt kind of satisfying. Another way you could have thought about this was how many choices are there for the first one, how many choices are there for the second one, etc. And that is the same thing as 3 factorial that I just defined. Okay, and so yeah, if you're going to arrange n distinct objects when order matters is n factorial. You can get the factorial button on your calculator. On the calculator, it is menu, I've got the calculator right now, menu 5 for probability, and then factorial is the very first thing. Menu 5.1 gets you the exclamation point on your calculator. All right, number of ways to arrange R out of n distinct objects when order matters is this. Okay, this stands for permutation. It doesn't stand for probability, it stands for permutation. This is like if you had to arrange, I think we did this with the letters in the word English just a minute ago. If I had 7 objects and I was going to arrange 4 of them, this would end up being 7 times, what I can count, 7 times 6 times 5 times 4. The 4 doesn't mean that I stop at 4. The 4 means I'm doing 1, 2, 3, 4 of them. If I did something like 6p2, that would be the first 2 numbers of 6 factorial. That's how that works. So it's like I've got 6 objects to arrange. I want to arrange 2 of them. There's 6 choices for the first one, then there's 5 choices for the second one. Here's the formula for that. What's happening here is I have the full n factorial on the top of this fraction, and then I cancel out a number of them. Let's go back to this 6 times 5. This would be 6 times 5 times 4 times 3 times 2 times 1. But then I'm going to cancel it out with 6 minus 2 is 4. 4 times 3 times 2 times 1. And that's why it ends up looking like the way it does. So I think the formula is actually kind of complicated to think about. I think that it's easier to just think, okay, I'm going to take the first R members of n factorial. And that's what's going to end up happening. Anyway, the calculator does this too. This on the calculator is menu 5, 2. And then if you do menu 5, 2, you get this, NPR and open parentheses, and you'd have to enter in the 2 numbers you want to put in for N and R. We will do this in class, but that's just quickly where that comes from. How many permutations are there for the letters in the word Tampines? That's 8 letters. If we're just rearranging them, there's 8 factorial. It's like I'm taking 8 things and rearranging all of them. That's the same thing as saying 8p8. Which, okay, fine. And it's a very large number. 8p8 is, I'm in the calculator right now, it's like 40,000. Yeah. Determine how many arrangements there are of 2 letters from the word golden. Okay, so there's 6 things. I want to arrange 2 of them. Chapters, there are 8 things, and I want to arrange 3 of them. And wealthy, there are 7. It's the hardest part about this. I got to count how many letters there are. That's 1, 2, 3, 4, 6, 7, P4. And those answers are, well, that's 30. I can do that in my head. 8 times 7 times 6. It's almost faster to type 8 times 7 times 6 than to do the whole thing. 7, 6, 5, 4. We just did this in the last page. Okay. Okay, first wrench in the gears they throw in here is what if we have some of the same letters repeating? What if we have a word like this? Okay, they're gonna make it a little bit easier first and say, well, what if we're just talking about before we start putting in repeats? Let's go back to the beginning. What if there's not repeats? Just the word rows. There should be 24, and they actually list them all here, which is kind of helpful. Here's the sample space of all possible rearrangements of the word rows, which you would expect, yeah, to be 4 times 3 times 2 times 1. But all of a sudden we change it to Ross. Now what's going to happen? There'll be some that all of a sudden start looking like each other. Because if I flip the 2 S's, it doesn't make a difference, right? It doesn't look different. So here's an RSSO. There's another RSSO somewhere else. Of course, I picked one I didn't see right away. Oh, they did that because we've already seen it. Okay, that's right. And RSOS, they took that one out because we've already seen it. How many repeat? How many do we have left? Well, if we count how many have repeated now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now there's only 12. A bunch of them have kind of fallen off. So, yeah, and then what happens if we had 3 S's? Then a whole bunch of them kind of come away. And there's all these repeats. We're only left with 1, 2, 3, 4, right? That could possibly even look different. It's about basically where you're going to put the R, because everything else looks the same. So now we're down to 4. So notice what's happening each time. We kind of had to divide this one by 2 when this happened. And then from the beginning to down here, we had to kind of divide this one by 6. Yeah. Think about what's kind of going on there. This is what's going on. So every time we have to arrange n objects, we have to kind of discount the ones that look the same by the number of ways that the identical ones can be rearranged. So you do one of these for every time you have a, this could be easier to actually show you examples than to explain this, but every time there's repeating letters, you have to kind of, again, discount or kind of divide by the number of ways things are going to repeat and show up the same way again. And you do one of these factorials for every different letter that there is and how many ways it can repeat. So what happened here was was 4 this was 4 factorial. This was 4 factorial divided by 2 factorial, which is why we divided it by 2. This was 4 factorial divided by 3 factorial, because the thing repeated. There were 3 identical ones, and here there were 2 identical ones. We never had to use a B or a C. That would happen when you get like multiple S's and multiple T's or something in a word. You'd use a different one of those for every one of the different letters that repeat. So that's what's going on here. So here we have, this would be 6 factorial, but there are 3 E's that look the same. Oh, should I do that? This is 6 times 5 times 4 then, because 3 times 2 times 1 has been divided out. This is 120. This one, Mississippi, has 4, 8, 11 letters, but we have 4 S's that repeat, and we have 4 I's that repeat, and we have 2 P's that repeat. So that's what that A, B, C means. Those are different letters and how many times each one of those repeats. The I's and the S's look different. So it's not like I just want to take all the repeats and put in one big bucket and divide by that factorial. No, I divide by a different factorial for the different letters that repeat themselves, if that makes sense. So let me do this on the calculator. This is going to be kind of more to think about. My computer's freezing up. All right, so it's 11 factorial divided by 4 factorial times 4 factorial times 2 factorial, which is still a lot, 34,650. I'm putting those answers there because, well, first of all, I want you to show actual answers. And I want, during this video, if you want to try practicing on your calculator, see if you get the same thing, because some of these buttons are new. Okay, combinations is the other side of the same story. Permutations, combinations is kind of something we should always talk about on the same day. Combinations is the one where we don't care about the arrangement. So A, B, C, and C, B, A are actually the same. So like hands of cards, this is a good example. When you get a hand of cards in most games, it doesn't matter which order you get them, especially games where, like Uno, where they deal all the cards at first. You get 8 cards or something at the beginning, or 7 cards. And then the first thing you do in your hand is you arrange them in the order you like. It didn't matter which order they came to you. You start playing those cards, any one you want, or strategically. The 7 cards are the 7 cards, and I'll say it this way: order does not matter at that point. So the number of, like, if I got these, well, this example they have here, if I was dealt these 2 different hands in these 2 different orders, yeah, they could possibly come to me in 2 different ways. But in the end, when I count how many different hands there are, those 2 things count as the same situation. Okay, how many ways can we arrange n different objects if order does not matter? Well, it's called combinations, NCN. Yeah, if we were going to arrange all of them, well, if there were 5 cards in your hand and you didn't care how they arranged, how many different collections are there? Well, there's only 1 collection. You only have the 5 cards. You're arranging all of them, and you don't care about the arrangements. That's kind of a silly question. That's why that's 1. But if you had to say pick out of 52 cards, you wanted to arrange, pick a collection of 5. How many collections of 5 can you get out of 52? It's now NCR. This is also in the calculator. It's menu. It's probably 5-2. Let me just check that. Menu 3. It was 1 in that menu. 1 is factorial, 2 is permutations, 3 is combinations, and that's probably all we're going to use that menu for. But then you get this NCR text, and then it opens a parentheses, and then you have to put the 2 things in for the N and R. Anyway, this looks a lot like permutations. That was permutations, and we're just multiplying by this other R. And that's exactly what we've been doing just now with the letters that look the same. So but now we're rearranging the whole collection because we don't care how they are arranged. So it's like taking how many different arrangements are there, and then we're gonna kind of discount or clump together, I should say, the different arrangements of the same collection. So now we're just counting the number of collections. All right, so first thing you gotta do, and this is what you're gonna find yourself stuck on lots of these questions, is does order matter or not? So again, is ABC the same as BCA in these situations, or do we want to count them separately? Okay, so there'll be a lot of these examples, and this will be good for you. Okay, and then find the number of possibilities and answer. And this is answer is NPR, NCR. You don't have to actually do it, so that kind of helps. Do we care about order in this one? Cash and Walker are planning trips to 3 countries this year. There are 7 countries they would like to visit. One trip will be 1 week long, another 2 days, other 2 weeks. This last statement is just here to say, yeah, the first trip is going to be, yeah, the first country is going to be 1 week, the second country is going to be 2 weeks, or the third country is going to be 2 weeks. 2 days. In other words, the 3 trips that they kind of try to put in the 3 different time slots would be different if they rearranged them. So when you're making different assignments or you're putting people into chairs, kind of, and that's kind of what's going on here. Not that we know exactly which trip is going to happen first, but you know, New Zealand the 1 week is different than New Zealand the 2 days. So we do kind of care which vacation slot that it gets, if that makes sense. So this is a permutation. This is 7p3, and we can just number there. Because that's all they wanted. If you wanted to know what that is, it's 7 times 6 times 5. 25 people are going to run a race. The top 8 finishers advance to the finals. When you run that race, do you really care if you're 5th place or 6th place at this point? Not really. You would care in the finals, but this is like a qualifying thing. So we just kind of want to count how many different ways can you have a collection of 8 out of the 25. So this is going to be a order doesn't matter. Yeah, it's a different kind of outcome, I guess, when those top 8 are arranged in different ways. But this question is implying we just want to know who gets to go to the finals. If it's about who goes to the finals, we don't care what order they finished in. We just want top 8. A team of 17 softball players needs to choose 3 players to refill the water cooler. Who cares who's first to fill the water cooler? We don't care about that. We just need a collection of 3 out of 17. If it's like 17 softball players and you want to care like who's first base, second base, and pitcher, like that, those are 3 different jobs. So yeah, but this is just one job that takes 3 people. 10 students wants to elect 3 different named offices. Yes, those are different because those slots have names. That collection of 3 people could be kind of seated 3 different, in different orders. So we do care about that order. There are 15 applicants for 4 jobs, and the jobs have names. So we do care again. That's going to be permutation. Okay. This already feels like it's going to be long. I'm just going to apologize for that now. But it's good stuff, and you might want to watch this again. 5 cards are dealt from a deck. How many different hands are possible? Oh, yeah. Well, you're going to get used to seeing this a lot. This is, wow, I lost my, okay. 50, my hand hit a button there. 52C5. Okay, all the card questions, or a lot of the card questions are going to start with 52C5. So that's going to be the denominator of all these questions if we ever get to probability. How many hands have all diamonds? Well, imagine like you've already just talked. It's like a conditional probability. Like given that they're all diamonds, so it's like we're thinking about this new sample space now. The sample space has just been reduced to diamonds. There's only 13 diamonds to choose from, and 5 of them are going to be in your hand. 3 kings and 2 queens. From the 4 kings, I got to pick 3, and from the 2 queens, I got to pick 2 of them. That's all the ways there are to fill up your hand with those cards. And again, we're not doing probabilities yet because these probabilities are really rare, like especially this one. We're just counting how many hands have these things. These would be the numerators of what's the probability you're going to get them. And yeah, they're pretty small. 4 tens. Oh, I'm kind of skipping around here. I'm going down the left column. 4 tens. I have 4 tens to choose from, and I got to get all of them, so that whole thing equals 1. But wait a second, this is out of 5 cards. How many of these 5-card hands, and they're talking about 5-card hands. So far I haven't had to worry about this because that fills up the hand and that fills up the hand, right? I had all diamonds, 5 diamonds in the hand, or 3 kings and 2 queens, that fills up the hand. Here I have 4 tens, but lots of hands have 4 tens. Well, not that many. A lot of hands have 4 tens, and they have another card. So how many hands are there that have 4 tens and another card? I got to count for all those other cards. You might start to see this now. This might start to feel like a thing. When you're counting these 5-card hands, notice these numbers each time have to add up to 5. I have to account for collecting 5 cards. And so far, those have all added up to 5. Okay, let's keep track of that. 4 black cards, so those are going to come from 26. Need 4 of those, and 1 red card. The other red card's going to come from that. 3 kings, okay. From the 4 kings, I get 3, but then I need another card. How many other cards are remaining? 48 cards are not kings. I need 1 card that's... Oh, wait. I need 2 cards that are not kings. Yeah. 5 cards of the same suit. Okay. So I did the diamonds before, and that's going to be part of this, right? So I have... That would be like the 5 cards that are all diamonds. But they could be diamonds, they could be clubs, they could be spades. This is like the rearranging that with the letter G earlier. There's 4 different lists of these that are all 13C5. I should probably do all these answers, but I know this video is going to be long anyway. So for now, I'm just showing work. I'm maybe not going to show all the answers anymore. Because now we're just on the second half of this video, and I think it's already kind of long. Can we do this warm-up stuff in class? Sorry. Oh yeah, we'll do this in class, and this might be kind of a kind of a big, not waste, but a blast from the past. Simple probability. Yeah, this is gonna go easy. What's the title of this one? Yeah. Yep. Probability. I think we could do this together in class. I don't think I need to do this now. We also talked about complements. Sometimes the not occurring is easier to calculate. Wow, that page was easy. Because again, this is stuff we've already done. Independent, dependent events, done it recently. Yeah, blocks out of a box. Like I don't think. Oh gosh, are any of these new? No, I don't think so. I think this is all stuff we've done together. I don't even know if I need to do this in class. This is like total. I'm gonna put a big question mark on this. If we need, I'll think about this later. Do we even need to do that in class? Because that's so much like what we just did. Yeah, I think these are all repeat. Another big question mark. Should we do this in class or not? Maybe I'll like take requests. Do you want to do those? 5. Okay, here we go. Let's go back to cards. This is a little more interesting. 5 cards are drawn at random from a well-shuffled deck of 52. What's the probability? We haven't done probability with these yet. So the denominator on these, and I will actually calculate these with the calculator, because that's kind of a common thing. And let me just do this first. 52C5 is a pretty big number, but it's pretty common. You're going to see this a lot. This is out of how many different 5-card hands are there? 2, 5, 9, 8, 9, 60. That's 2.5 million. That's why cards are interesting. Okay, all hearts. We already did this once. 13C5, and you might think that there's a nice way to kind of reduce that. I guess there is, but it's not fantastic. Anyway, if I figure this one out, this is 1287. 1287 out of that other huge number. Yes, reduces as a fraction. It's 33 out of 66,640. So yeah, it does reduce. A lot of these will reduce a lot because of it's a lot of the same, strings of numbers we're multiplying. Exactly 2 hearts. Okay, so out of 52C5, exactly 2 hearts. That's 13C2. But then the other cards have to be non-hearts. So these other 3 cards have to come from the 39 cards that are not hearts. All right, do I have to keep doing this? Maybe I should. Okay, so on that one I get 9139 out of 16660. Okay, exactly 1 diamond, 2 hearts. Okay, 1 diamond. That's how I get a diamond. 2 hearts, 13C2, and the Queen of Spades. Well, the Queen of Spades is 1 card, and I need it. And then that's only 4 cards so far. So now I need to pick the other card from all the cards that can't increase any of these things. So I can't pick another diamond. I can't pick another heart. So that took out 26. Well, I can kind of look at this, right? There's 27 cards here that it can't be. So there's 25 cards left that it could be out of 52C5. And that is 65 out of 3, 3, 3, 2. See if you get the same thing as me. At least 1 club. Okay, I was waiting for these in some of those box and block questions earlier. I thought maybe marbles out of bag would give me at least 1. At least 1. I wish we would have seen this earlier. The best way to do at least 1 is 1 minus the probability of none. At least 1 is really hard to add up to. At least 1, we have to add up all the possibilities of getting exactly 1 club, plus all the possibilities of getting exactly 2 clubs, plus all. That would take forever. It's a lot easier to say, how do we fail this? And let's do the 1 minus probability of that. So everything but no clubs is at least 1. That's a lot easier because you could have 0 or 1 or 2 or 3 or 4 or 5 clubs if you think about it. And if I really want to know what's the possibility of 1 or 2 or 3 or 4 or 5, I just have to take everything minus the 0, the probability of 0. So let's do that. 1 minus, okay, then for no clubs, it's going to be 52C5, and I have to take all the non-clubs and pick 5 of them. That's not that bad of a calculation. It turns out to be 2,000 something out of 9,000 something. So, playing cards, if like say you're, for whatever reason, you really want a club and you keep getting cards, you're like, what are the chances I'm not going to get any clubs at all? It's actually, kind of low. It's 20% or so. Anyway, there you go. Game is played where a fair-sided die is tossed and a marble selected. There's a lot of complicated stuff going on. Yeah, we should probably do this together. What's the best way to tackle this problem? Combinations or a tree? I would say tree, because we have a die and then a marble, and there's stuff going on. So let's do this tree. The tree is going to be something like this. We're going to have die first, and the die can be 3 or 5, which takes us to bag M, or it could be something else, 1, 2, 4, 6, and that takes us to bag N. So this is a 2 out of 3 probability, and this is a, 2 out of 6. I was thinking 2 things at once. This is 1 out of 3, and this is 2 out of 3. And then bag M is 3 red and 2 green. So this is 3 out of 5, 2 out of 5. N is 2 red and 8 green. So this is 2 out of 10 and 8 out of 10. Okay, once I have that, maybe we should do the rest of this in class. What's the probability that bag M is selected in green? What's the probability of green and, yeah, let's do this in class. Okay. We will do the rest of that in class. This looks like something from Algebra 2. Okay, getting down there. Oh, yeah, this is repeat. So this is in general. This is the general rule for OR. This is the general rule for how you find OR. If it were mutually exclusive, it did not include that, which should not be a big surprise. If it's mutually exclusive, then that little part here, that equals 0. So this still works for mutually exclusive. It's just kind of silly. So for mutually exclusive, you can stop there. But it does work in general, and it works especially when there is overlap. If it's independence, we talked about both these. These are 2 little tests for independence. If we have independent, then you can just multiply it to figure out the and. If they're not independent, there's a general rule for you know what? Let's say in general. Let's just put it all on the same page. In general, if you're trying to find the probability of A and B, you probably see me do this a lot by now. It's the probability of A times the probability of B given A. Yeah, I can do that because that would be the same thing as B in independence. Okay, so there's a lot going on there, but this is all review. All right, 350 students, Venn diagram. Do I need to do this? No, we can do this in class or not. I might actually skip that one. Yeah, good. Lots of repeat. Yeah, in fact, we may have done the exact same problem. Okay, let's do a Venn for these. These are a little bit harder, and one more of these isn't going to kill us. So A is 1/2, B is 1/3, and that's all they tell us. Or sorry, that's I don't really know a lot about if they're independent or not yet. A or B is 3/4. So one way to say that is I know the outside here is going to be 1/4. So yeah, filling out the rest of this Venn diagram is something I feel like, yeah, I should do this because we haven't done this a whole lot. If I added this all up, 1/2 plus 1/3 plus 1/4, that should be bigger than, or that's possibly going to be bigger than 1. I think it is bigger than 1. 1/2 plus 1/3 plus 1/4. Yeah, that's 13/12. 1/2 plus 1/3 plus 1/4. That equals 13/12, and that's too big. That tells me that there is some overlap. I've counted something twice, and that something has to be here. And that something has to add up to 1/12 because that's how much bigger than 1 I am. Okay, so 1/3, I could fill out the rest of this Venn diagram while I'm at it. 1/3 minus that is going to be, 1/3 minus 1/12 is 1/4, strangely enough, right there. And 1/2 minus 1/12 would be 5/12, I believe. Okay, are they mutually exclusive? No. 1/12 in overlap. Or actually, I should say it this way. The probability of A and B is not 0. It's 1/12. Independent events. Well, let's see. The probability of A and B I know to be 1/12. The probability of A times the probability of B turns out to be 1/2 times 1/3, which is 1/6. These are not equal, so no. All right. We have this Sharon and Lisa thing. This looks like a tree. Or actually it could be a Venn. Yeah, I kind of like the tree idea. Yeah, let's do the tree. So Sharon cooks dinner because once we know about one thing, it kind of drives the other one. If Sharon cooks dinner, the probability they have pasta is this. If Lisa cooks dinner, the probability, yeah, okay. So first is who's cooking dinner, Sharon or Lisa, and then it's pasta, yes or no. Okay, so Sharon cooks dinner is 0.75 here. And Lisa cooks dinner, it's 0.12, 0.88. Sharon cooks dinner 3 nights out of 10, so this is 0.3, 0.7. I think, you know what? I think the rest of this we should do together. I don't need to waste your time on that. Last question on this page. Actually, last question of the whole thing, right? Athletic subcommittee, 7 council. Okay, this looks like permutation combinations. How funds raised should be spent on sports activities. There are a total of 15 council members, 9 males, 6 females. With probability the subcommittee will consist of only exactly 3 females. Okay, it's probability. So how many different committees can we make? We're trying to make 7 out of 15. So is it 17P7 or 17C7, first of all? Well, we're just trying to make a committee of 7. This committee doesn't have like vice president, president, secretary, treasurer. It's just 7 people out of 15, so we don't care about the order, essentially. So that's the total number. So that's going to be kind of the denominator. Maybe I should have written that as kind of like a denominator. That's going to be the out of. So out of 15C7, how many of them are exactly 3 females? Okay. So this is like cards, kind of. Out of the 6 females, I have to choose 3, but I also have to fill out the rest of the committee. Like this part of the list is gonna repeat for all the different collections of males that will make the rest of the 7 people. So I need 4 males from the 9 that exist there. So let's figure out this probability. And I get this. And you can actually just type all this into one fraction on your calculator. So it looks basically just like that on the calculator. It totally works. 56 out of 143. So it's quite a large probability. It's about a third. Okay, I will see you in class. That's enough for this.